In this video, we will verify through simulation the analysis and calculations we did corresponding to the example problem on a two-pole grid-tied inverter. We'll also look at various waveforms in order to better understand the steady-state operation of a two-pole converter. The example problem considers a two-pole unipolar PWM converter that interfaces a DC voltage source of 450 volts to a single-phase AC grid with 340 volts peak. The filter inductance along with the grid inductance is given as 2 millihenry, and the corresponding series resistance is given as 0.1 ohms. And for this converter, we need to do the calculations for two cases. One is power flow of 5 kilowatt from the DC source to the AC grid at 0.866 lagging power factor, and the second case is the reverse power flow corresponding to power from the grid to the DC source, again at 5 kilowatt but at unity power factor in the case 2. And for each of these two cases, we needed to calculate the control voltages for the two legs VCA and VCB, and also calculate the value of the average DC link current for these two cases. Okay, so we used phasor analysis to calculate the various quantities of interest. So for case 1 of 5 kilowatt from DC to the grid at this lagging power factor, we used the grid voltage as the reference phasor 340 angle 0, and for the given power and power factor, we calculated the grid current to be this phasor. So now when we do the simulation, we will verify that the grid current comes out to be exactly this sine signal of 33.96 amperes peak, and it lags the grid voltage by 30 degrees. These are the phases for the resistive and inductive voltage drops, and once again we will verify, for example, that the average of the inductive voltage is 25.6 volts peak and has this angle with respect to the grid voltage. Okay. Now once we have these three phases VG, VR and VL from the average model, the pole converter output, the converter output voltage VAB is given as the sum of VG, VR and VL, and that comes out to be this quantity. Okay. This is also something that we will verify in simulation. So once we get VAB, the control voltage is simply VAB over VD, and in time domain it is the sine signal 0.792 peak, and it leads the grid voltage by this small angle 3.3 degrees. Okay. It's not written here, but VCA we have to give it as simply VC, and VCB we have to give it as this minus VC. Okay. Then we also calculated the average DC link current, which is again from the transformer model, average model. The DC link current is simply the turns ratio, which is the control voltage VC times the grid current IG, and it turned out to be this quantity. It has a DC component of 11.24 amperes corresponding to the 5 kilowatt power, and this is the pulsating component at twice the line frequency, and its magnitude is here. Okay. So this we'll apply this control voltage as per this requirement and verify that the power is exactly this, the grid current is shown here, and that the DC link current comes out to be this expression. That is our objective. Similarly, for the case 2, power flow from the AC to the DC side, we calculated these quantities. So the current is shown here, which is something that we'll verify, the inductor voltage, the converter output voltage, and we need to apply this control voltage in order to get this condition. And the DC link current again was calculated to be this expression. Once again it has a DC component, negative in this case because the power flow is into the DC source, and this is the pulsating twice the line frequency component. Okay, so this is the Plex schematic corresponding to this example problem. Let me just zoom in on the power stage first. Okay, so that's the two-pole converter. You can see the pole A and pole B here, the full bridge structure, the DC voltage source set at 450 volts DC, and here is the filter inductor connected to the grid at 340 volts peak, and the filter resistance is 0.1 ohms, just like our example problem. Now coming to the PWM stage, So this is my control voltage. So looks like I'm simulating the case 1 corresponding to 5 kilowatt power from the DC to the grid, and the control voltage that we calculated was this sinusoidal signal of 0.792 peak value, and it was to lead the grid voltage by this angle 3.29454 degrees, and this is at 60 hertz. So we generate this sine wave and apply that as the control voltage. For unipolar PWM, VCA is simply this control voltage VC. So that is given directly to this the PWM block, which is nothing but a relational operator, meaning if this first signal, the control voltage, is higher than this triangular waveform, the output is 1, and that goes to the top switch, the switch here as its gate drive, and the inverse of that is through this NOT gate. So G2 is given as the gate drive for the lower switch of pole A. Okay. Now similarly for leg B, we need to compare minus VC with the same triangle to get the corresponding gate drive for the upper and lower MOSFETs. So VC is multiplied by minus 1, that forms VCB here, controlled with the same triangular waveform, and the output is given as the gate drive for the top switch of pole B, and its inverse is for the bottom switch. The triangular wave is goes from minus 1 to plus 1, and it has a frequency of 20 kilohertz, which is the same as the switching frequency of this two-pole converter. Okay, and the rest of the circuit, let me zoom out. So these and what is shown here, they are all scopes and probes for monitoring, looking at various waveforms. So I will explain each one of them as we run the simulation and begin to start looking at these various scopes. Before that, okay, I should also talk about this other control signal. So what I have here corresponds to what we calculated for case 2, another sine wave with a lagging angle. So when I simulate case 2, I would just delete this connection and connect this as my control voltage. Okay. But for case 1, you're using this control signal that we calculated corresponding to this DC source to grid power flow. Another thing that I should mention before we go into simulation is to give appropriate initial condition for this inductor current, the only state that we have in this example problem. So if we give the correct initial condition, then we will reach steady state immediately, right from the beginning, and reduces the time for which we need to do this simulation. Okay, so the first set of waveforms that we will look at corresponds to this grid current. Okay. So for case 1, we calculated the grid current to be this peak value of 33.96, sine wave at 60 hertz, and lagging the grid voltage by 30 degrees. So this signal is only for verification, and it is not part of this actual simulation. So this is being compared with the measured grid current. So I put an ammeter here in this grid current path and call that as IG and plot that here. So this measured IG is being compared with what we actually expect from our analysis, and we also need to verify that this current lags the grid voltage by 30 degrees. So in order to do that, I also plot the grid voltage, but the grid voltage is 340 volts peak, whereas the current is only about 33 amperes peak. So to put them in the same scale, I just scale the grid voltage by this quantity so that I can look at both the waveforms in the same plot. Okay, so let's run the simulation. Simulation start, and look at these parameters. Okay, so these are the grid current waveforms. So this blue waveform here, that is the grid voltage shown for reference, and there are actually two waveforms, red waveform, and within that there is a green waveform. So the red waveform, where you can see a switching frequency ripple, that is the actual measured grid current, and the waveform inside that is the one that we're using for verification. So what it tells us is that the control voltage that we calculated and applied in this simulation is correct. Therefore, the grid current exactly matches with what we calculated for this 5 kilowatt power flow. Okay. So let me and also you can see that the current actually lags the voltage, and we can show that to be exactly 30 degrees. Okay. Because the signal that we applied for verification was at minus 30 degrees lagging angle. Therefore, the actual grid current also is shown verified to be lagging by 30 degrees. So let me just zoom in on these current waveforms. So if I zoom in here, so you can clearly now see the switching frequency ripple in the grid current. And inside that you see this green waveform, which is the signal that we use for reference, and clearly the grid current exactly matches with the required current value. Okay, the next waveform that we are going to look at is the actual converter output voltage, this VAB, which is a switching signal at actually twice the switching frequency because of unipolar PWM. So VAB here, that's a switching waveform, and along with that we are also plotting the cycle by cycle average value of VAB. So the CCA, this block calculates the average over one switching period, and so that is monitored in this scope. So what we expect for the average for the VAB is this quantity, sine wave at 356.33 peak, and it should be leading the reference by 3.3 degrees roughly. Okay, so these are the simulated waveforms. The red waveform is the instantaneous VAB. It is switching. First of all, this is unipolar PWM. So during the positive half cycle of the 60 Hz waveform, all the pulses are positive, and during the negative half cycle, all the pulses are negative, switching between minus VD and 0. Okay. Now, so we required this VAB average, the fundamental component, to be 356, I believe, peak value, and that is verified here. You can see this is roughly, or should be exactly what we calculated, about 356 volts peak, and it should be leading the reference by about 3.6 degrees, and that is kind of verified. If you look at t equals 0, the green waveform does not start at exactly at 0. There is a small positive value here. It can also be verified by looking at the end. So this is what is shown as 3 complete 60 Hz cycles from 0 to 50 millisecond, and you can see this small positive portion here, so which means that the fourth cycle has started slightly before the 50 milliseconds point. So this waveform is really leading our reference grid voltage, which has the angle of 0, the reference phasor. So that verifies. Now if I zoom in near the somewhere near the peak, the positive peak of this VAB waveform, zoom in further here, you can now clearly see the switching pulses. So the red waveform is switching between 450, which is our V sub VD DC link voltage, and 0 in the positive half cycle. And if I go to some negative half cycle, so it takes some time. Okay, so this is the negative peak. Again, clearly you can see that the pulses are now switching between minus 450 and 0. Okay. And the average of that is not sure if we zoomed in exactly at the negative peak, but you can see it is around this minus 356 that we expected. Okay, so the next waveform that we are going to look at is actually the DC link current. So before we look at the simulated result, let me just show what we are expecting to see. Okay. So the calculated DC link current, it was calculated to be the turns ratio of our ideal transformer in the average model times the measured grid current. So ID is average is VC times IG, and it came out to be this DC value of 11.24 and this twice the line frequency component, okay, at 13.45 peak. So let's go to the simulation and see if this is exactly what we're getting. Okay, so in simulations, these blocks correspond to the DC link monitoring. Okay. So I'm plotting in this scope the DC link current obtained by 3 different means. Okay. So first of all, we are interested in the average, the cycle by cycle average of the DC link current. So I measure the DC current, the DC link current here with this ammeter, and call this current as ID. Okay. Then that ID is passed through this CCA block, and out comes the cycle by cycle average value of this DC link current, IDCCA. That is the first waveform. The second waveform actually comes by the multiplication of the instantaneous control voltage, which was the turns ratio of our ideal transformer in the average model. So the turns ratio times the measured grid current, so that should also be exactly equal to the average value of the DC link current. So just for verification, I'm also plotting that. And finally, so this is what we calculated in the analysis that I just now showed as a PowerPoint slide. So this is the expression for the expected average DC link current. The DC component is 11.24, and this is the twice the line frequency component with a peak of 13.45. Okay. So if everything is right, then each of these three waveforms should be exactly the same. And let's see if that's what we get. And go ahead and simulation start. Okay, so these are the three versions of the DC link, average DC link current. So there are actually three waveforms, and the fact that they are almost superimposed on each other verifies that our analysis is correct. Okay. So before I go into each of the three ones individually, let's just look at the general wave shape. So this is a DC link current, and the zero line is this one. So we can see that for a small part of the sinusoidal waveform, the DC link current is actually negative. So that corresponds to the 0.866 lagging power factor that we analyzed. Okay, so the scale here on the x-axis is from 0 to 50 milliseconds. So in 50 milliseconds, we actually have 6 cycles. So therefore, the frequency of this DC link current average is 120 Hertz as we expected, plus a DC component. You can see the offset. So the zero line is here. So there is definitely a large DC component. Okay. So let's zoom in to see the three versions clearly. Zoom in further. Okay. All right. So the blue waveform, where you can see the high frequency ripple, that is the product of instantaneous VC, the control voltage, and the grid current. Now VC is a smooth sine, whereas the grid current has a high frequency ripple. Therefore, the product has this high frequency ripple. The red waveform is the that comes from the expression that I wrote in simulation, which corresponds to what we derived in the example earlier videos. The one with the DC component and the twice the line frequency component. And the third waveform, the black waveform, that is obtained by actually measuring the instantaneous DC link current and taking it cycle by cycle average. Okay. So clearly that matches very well with our analytically calculated red waveform, and they both match with the VC times IG method as well. Though it's not shown here, it's it's easy to see that there's a large DC component. Its value is I think it's 12 point something, and if you remove that, what we will end up is just the 120 Hertz sinusoidal waveform with a peak of around 13 amperes. Okay, so some of the other waveforms for case 1, as well as the complete set of simulation waveforms for the case 2 of reverse power flow, that we will take up in part 2 of this video on simulation of this example two-pole converter.